Hello everyone, I'm ArdaŞenyürek. I'm majoring in mechanical engineering and I'm second year student in my department. For the sake of the project, I'm going to be performing the analysis of the table in dining hall of the Bilkent. Let's get started. First of all, I modeled the table so that I can work within the digital environment. Here you can see the dimension, the picture of the model. Here is the dimension of the bar between the solid bars. It is 57 centimeter length and 2.5 centimeter in diameter. As you can see the height from the reference point. Here you can see the dimension of the solid bar. Here you can see the rectangular supports at the bottom of the assembly of the table. Support solid has the shown dimension 7.5 centimeter in diameter and 70 centimeter in height. Here is the geometry under the table. As you can see the dimensions of it. Since the geometry of the rectangular support is too complicated actually to work with, I simplified it to have some like basic rectangular shape. As you can see the dimension of the upper table dimensions, the upper table it has 5 centimeter width actually. The tray dimension is shown. To simulate the tray that exerts a force on the assembly, I used the external loads as a distributed mass with a some value. The value is 2.5 kilogram, and I applied distributed the mass over the region of the tray area, and then I simulated the mass exerted by the table itself as an 25.36 kilogram over the region of the entire upper table. Then I simulated that and gathered some plots from that. Here you can see the stress plot. Here you can see the stress plot beneath the table. Here you can see the stress concentration being very high at the edges of the solid bars. Actually, it is something that we covered during the lecture, that if you have sharp corners, you're gonna have some really high stresses. Since, by the way, there is some bending, you can see some stresses going on there. Here you can see the displacement plot. Here you can see the displacement plot. Actually, the bending, you can see the bending actually. The elastic curve has derivative of 0 in the fixed places, by the way. It's worth mentioning that. As you can see the strain plot being very high at the location of the support bars and edges of the rectangular supports. Is measuring dimension section. I measured dimensions with Apple's AI measurement system and as well as the conventional measurement methods. As you can see the dimensions of the rectangular supports at the bottom of the assembly, at the bottom of the table. As you can see the upper table dimensions. Here you can see the bars dimension, the whole assembly actually. I approximated that it as being 70 centimeters, since there is a small gap that I didn't measure. I calculated the displacement, strain, and stress analysis of the solid bars. The vertical solid line, solid bars. To do so, I started with a few assumptions to work with. Let's see. let me show you the. Okay, we are in record. Assumption 0 is tray mass with some food has 2.5 kilogram. Assumption 1 is rectangular table is made of cherry wood. Assumption 2 is support bars. Support bars are solid. Assumption 3, the bars are made of alloy steel. Assumption 4, the assembly is symmetric. Assumption 5 is all materials in the assembly are isotropic. This is kind of crucial since we gotta take the E and these denominator out of the integrand. Using the assumption 5, I take the denominator out of the integral, and using the assumption 4, I give the justification why I will work with one of them, just one of them, because this is exactly symmetric. I don't need to work with two of them. I expressed the equilibrium of table and used the equilibrium in y direction, and I gathered the F2 as you can see, and find the expression of the average stress as a function of x as this one. And since the SolidWorks neglect this term, I will be neglecting this when calculating the average stress and comparing with the SolidWorks plots. And it turns out to be same, by the way. I did the same thing for the displacement, and I found the displacement as this and strain as this for the SolidWorks part, and without without neglecting this term, I found the actual displacement as this, and same reasoning as this. By the way, these values are all same with SolidWorks plots values, so it is reasonable results. I did a brief shear stress analysis of the on the table and the bottom support rectangular supports, and I found the tau average shear average as this one. Since tau yield is 11.7 megapascal, we are in a safe spot. Using the this relation, since we are in elastic region, I can find the shear strain actually to be this one. Let's see. For the same reasoning, I found the shear average as this. Let's see the plots on action. Thank you for watching and listening my presentation. Have a good one.